Okay. So, in the previous class we have talked about few fundamental aspect of communication. So, now we are into pulse modulation, so specifically pulse amplitude modulation. So, let us try to see if we try to employ a practical pulse modulation. Okay. So, let us say I have a signal which looks like this. Okay. I want to do a pulse amplitude modulation, but remember the pulse is no longer a impulse like the one we have taken impulse trend for proving our Nyquist theorem. So, it is not, it is unlike that. So, let us say the pulse might have some shape, it has this shape and we are calling this as Pt. Okay. Correspondingly, we will also have a Fourier transform of this which let us say it is some Pf which is there. Okay. So, it might be anything, it might be band limited, it might not be band limited. So, that depends on the pulse, the shape of the pulse. Okay. So, let us say we have we know this. So, there is some pulse and we know the corresponding frequency response of that pulse. So, we are trying to make this analysis generic, so that for any pulse you put this will be true. So, we can have pulse like this of finite duration, then this will be just a special case of that Pt. We will try to see these things later, but right now we are saying any pulse, any Pt which has a corresponding Fourier transform which is Pf. Okay. So, these two things are known. So, basically what we are doing, we are again sampling it, but now and the sampling intervals are again related to that Nyquist sampling interval and all those things. Okay. So, that is there, but now what is happening, this particular part will be multiplied by this kind of pulse similar to Pt, then this one there will be little less amplitude and so on. So, this will become something like this, here it will become something like this and so on. Okay. So, again the tip of the pulse basically construct your signal. Okay. So, this is what we are trying to do. Okay. So, let us try to see whenever we do this modulation what exactly we are getting. So, let us say we call this particular modulated pulse train, we call this as G tilde t. Okay. So, what is this? We are just taking a sample at every instance separated by Ts. Okay. So, we are taking samples and multiplying that whatever instance that whatever the strength of that sample with the pulse. Okay. So, basically our this thing will be represented as nothing but this G of nTs P whatever that pulse is T minus nTs, right. So, that is actually our this particular signal. So, basically what is happening, every time at a particular instance, suppose n equal to 0. So, that instance I get this amplitude, that multiplied by this P I get this pulse, the bigger pulse probably. Next instance at n equal to 1. So, I get GTS and then multiplied by pulse must be shifted by Ts amount. So, n equal to 1. So, it should be shifted by Ts amount and again multiplication. So, this is exactly what is happening whenever I means represent this pulse modulation. Okay. So, this is basically my overall pulse modulated signal. Now, P I can always write as pulse and then convoluted with delta, because I know any signal convoluted with delta remains the same. So, I can definitely write this as Pt convoluted summation n GNTS, that has nothing to do with t. So, therefore, this is just a constant thing, and the summation and the convolution can be means basically exchange. So, whether I write it inside the convolution or outside the convolution, it is all the same. So, basically delta t minus nts. Wherever the delta position is, p will be convoluted with that and create a pulse at that position. Correspondingly, the g nts will be multiplied and I get the same thing. So, I can have a representation like this. What we can see, what is this? This part we have already studied. This is basically the impulse sampled version. So, we earlier we have called this as g hat t. Okay. This is the impulse sampled version of the signal. Okay. So, I can write this g tilde t, which is actually means modulated with a practical pulse, which is this p t, which has a frequency response of p f. So, I get this. Okay. No problem in that. Now, let us try to see what will be the corresponding frequency response, okay, or if I do Fourier transform. So, let us say I call this as g tilde f, the Fourier transform of this one. So, that must be Fourier transform of this one. Now, it is convoluted in time domain. So, in frequency domain they must be multiplied. So, what was the Fourier transform of this? This was 1 by T s, we have already proven, and g of f minus n f s. Okay. So, this has been already proven. We have already proven that impulse means if we take impulse train and then multiply the signal with that or modulate the signal with that, we get this frequency response, where g is actually this g f is the Fourier transform of g t. Okay. So, this is something we know already, that is a band limited signal and all those things are there, and our f s is also following that Nyquist criteria. Okay. So, this is this part g hat t, that is the Fourier transform of that. P t I know p f. So, that should be my Fourier transform. So, this is the overall Fourier transform. Okay. So, this is something we have now understood, that if I basically try to modulate my signal with a realistic pulse, then the corresponding Fourier transform will be this Fourier transform, which was the original Fourier transform if I do it with an impulse, okay, with which we have proven the Nyquist sampling, and then we could show the interpolation that just by a low pass filter we can extract that signal out. Now, we are seeing that if we have a means non ideal or non impulse pulse train, then the overall Fourier transform has to be multiplied by the Fourier transform of that pulse. Okay. So, let us try to employ these things for a practical scenario. Let us say, of course, impulse I cannot generate, but I can always generate this kind of pulse, which is of finite duration. Let us say the duration of this pulse is T p, okay, where of course T p must be less than T s. Okay. That whenever I am constructing a pulse train, so basically this is the pulse, this is the next pulse. So, this between these two pulses the difference is T s, which is the sampling interval, and this is T p. Okay. So, then what is the corresponding P t? That is actually a box function. So, this is a box function of duration T p. So, of duration T p, and because this I take as 0. So, basically box function, this must be the central point. So, there is a 0.5 T p shift. So, I can write this as t minus 0.5 T p. Okay. So, this is my P t, fine. So, that happens to be my P t. Immediately what I can do, for box function I can always generate a P f, corresponding P f. This is something we can always do. So, what will be that P f? How do I get that P f? This is just a delay. So, if you can even ignore that, if I have my pulse described like this, then I can ignore that part. So, I can as well write it as pi t by T p. Okay. So, that means it is a box function which gets repeated, and that has a means sorry, it is not repeated, it is the single pulse we are describing. It is a box function centered around 0 and it has a width of Tp. So, basically it looks like this. Okay. So, it is defined from minus Tp by 2 to plus Tp by 2 and I have this condition satisfied. Okay. So, immediately if this is a box function, I will get a corresponding sinc function Pf. So, that should be Tp sinc 2 pi f Tp. Fine. So, this is my Pf. So, therefore, my G tilde f must look like Tp sinc 2 pi f Tp, okay, into 1 by Ts G f minus n Fs. So, this is what I get. So, what is happening if you just try to see in the spectrum. So, I have this structure which was the earlier structure as long as I satisfy the Nyquist criteria. So, it gets 1 by Ts down if this is my minus B to plus B, this is my Gf. So, it gets 1 by Ts down and this is still defined from minus B to plus B and it gets repeated after every 1 by Ts or equal to Fs. Okay. So, that is what is happening. So, this still remains. So, this is that part. This gets multiplied with this part. Okay. This is the disturbing part, because what will happen, how does this looks like? This is a sinc function. So, that must be, if I just draw it down, so that is a sinc function which is touching 0 at 1 by 2 Tp and minus 1 by 2 Tp. Okay. Now, what will happen? Sorry, it should be, I have done it a little bit wrong. So, it should be centered over here. So, let me draw it one more time. So, this is that thing and this is the center. So, this looks like 1 by 2 Tp, okay, and minus 1 by 2 Tp. Now, these two gets multiplied. If you see what is happening, earlier what we were doing, we were just putting a band pass filter, getting our signal back, but now my signal is a composite signal multiplication of these two, and unfortunately for me, this is getting multiplied by this, which does not have a flat characteristics over the entire frequency band of interest. So, what will happen? There will be, because of this multiplication, there will be a distortion to this signal which will be created. So, whenever we put a pulse like that, there is a possibility, now we have explored that, there is a possibility of distortion. So, what will happen once we multiply these two, probably it will look like these things will be little bit suppressed. So, it will look like this, it should be of course symmetric. So, a little bit of distortion has been created, it is not ideal for this one. I can still put a band pass filter of minus B to plus, sorry, a low pass filter of minus B to plus B, I get this signal back, which is actually a multiplication of these two. So, but our demand is this one. Okay. So, that is where we are having a problem now. Now, let us try to see how do I make this flatter. So, this will be flatter if this point where it is touching 0 stretches out. So, it goes away, then this almost looks like a flatter. So, if I just draw it, if this touches over here, that is minus 1 by 2 p 2 Tp and this is plus 1 by 2 Tp, then it becomes, so basically it goes and, so as it, now you can see within the band of interest it is almost flatter. So, whenever I multiply with it, the original shape will be intact. What this means? So, 1 by 2 p I am increasing, that means the Tp has to be reduced, right. So, what happens to the pulse? This is my Ts and I am trying to reduce the pulse width. So, this will be exactly flatter when I have the pulse which has almost infinitesimally vanishing width, okay, which is a impulse function again. So, I know that if it is impulse, then this will be completely flat and I do not have any distortion, but I cannot generate impulse. So, what I need to do is I need to generate a pulse definitely, finite width pulse, because that is what I can do, because then the energy will be restricted, but I need to also ensure that the pulse width should be as small as possible, because then there will be no distortion due to this modulation technique. Okay. So, this is something we have to keep in mind, and this corresponding sampling is termed as flat top sampling. So, let us try to see in time domain what is happening and why it is being called flat top sampling. So, I have this message signal, I do have pulse which are like this, some finite width pulse, and at every instance, suppose this is that instance, I take the sample value and I represent a pulse with that sample value. So, this is that. Next time I take another sample value and I represent the pulse with that amplitude of that sample value. Next time again I get another pulse and I get a. So, if you see the pulse with which we are modulating, the top of the pulse remains flat, because we have taken a square pulse. So, a box function, because the top of the pulse is flat and it just takes one instance of the sample value. So, the sampling looks like this. I take a sample, I maintain that, I take a sample, I maintain that. Okay. So, this is being realized in practical circuit by sample and hold circuit. So, basically what we do, we take a sample and we hold it for the pulse duration, and that is how the top of the pulse becomes flat, and corresponding pulse is called flat top pulse. This kind of flat top pulse is done by sample and hold circuit. Okay. So, which probably we will not be discussing that, because that is part of the circuit. If you just go and look for sample and hold circuit, you will get plenty of example of that, different realization of sample and hold circuit. So, with sample and hold circuit, people do this flat top means sampling or sampling with flat top pulses or pulse train. So, the disadvantage of this one is what we can see, that we need to really make sure that the pulses are very small, that is the first thing. Second thing is probably there is a corresponding distortion which is coming, and that is why probably we are making this pulse width very small. We have already demonstrated that 1 by Tp has to be very big, that means the Tp has to be very small. Okay. So, the pulse width has to be small, and with this whatever finite pulse width you take, there will be certain amount of distortion, because it is the overall spectrum is getting multiplied by Pf. So, that is giving distortion to the baseband signal as well, and whenever we low pass filter it, we will get some amount of that distortion. Okay. So, that is the disadvantage of this kind of sampling. Okay. Is there any other sampling? So, let us try to see if flat top sampling is one of them. Is there any other counterpart of this? That will be our next target. So, the counterpart of flat top sampling is called natural sampling. What is natural sampling? So, natural sampling is something like this. I have a signal, I have pulse train. Okay. So, where the probably this pulse amplitude is unity, assumed to be unity. So, it has, it is a pulse train. So, it has pulse from minus infinity to plus infinity. So, what I do in the previous one, I was taking a sample and then multiplying by that pulse. okay, or I was with that sample amplitude I was representing a pulse. Okay. So, just that pulse was getting multiplied by that sample amplitude. Here what I will do, this g t I will actually multiply with this means pulse train. So, let us say that is q t, okay, or let us say q t s t, because this is the t s. Okay. So, I will be multiplying it. What will happen? Wherever it is 1, it will be followed, because I am multiplying. So, because it will be multiplied by 1. So, this will be sampled all right, but during this duration it will just follow, because it is multiplication 1 with this one. So, it will just follow the way signal is whenever the pulse is on. So, it will just follow that signal. So, it happens to be this way. So, basically as you can see, you again connect these things, your signal will be regenerated. Okay. So, this is called the natural sampling. Natural sampling means within the pulse duration you are actually allowing the signal or the pulse shape or the top of the pulse to follow the signal. That is what we are trying to do. Okay. So, can you now characterize it in frequency domain and then try to see the way we have done for flat top sampling. So, that is something we will try to do. For that, first of all we have to characterize these things. So, q t s t, what is that? That is a periodic signal, right. So, if it is a periodic signal, I can always write in Fourier series. So, n from minus infinity to plus infinity, sum q n, or you can write it as d n the way we were writing, e to the power j n omega s t, where omega s is equal to 2 pi f s, where f s is 1 by T s, right, because that is the fundamental frequency. So, we will get this, where the q n, the way q n is calculated. So, that should be 1 by T s minus the pulse is defined. So, if this is the pulse from minus T p by 2 to plus T p by 2. So, from minus T p by 2 to plus T p by 2 it is defined q t e to the power minus j n omega s t dt. So, you just do this. So, if you just evaluate this, what do you get? 1 by T s, okay. And you have because this q t remains 1 within this. So, I will have 1 from minus T p to plus T p, because this is the pulse is having unit amplitude, that is what we have assumed. So, it is just e to the power this, you integrate it. So, you will be getting e to the power minus j n omega s t divided by j n omega s, and then putting minus T p by 2 to plus T p by 2. Okay. So, that is what we are getting. And then if we evaluate this, this happens to be okay. So, if I just do simplification after putting T p by 2 and minus T p by 2. So, I get 2 by n omega s T s e to the power j n omega s T p by 2 minus e to the power minus j n omega s T p by 2 divided by 2j. I have taken this form because it will be a sine function. So, I can write 2 by n omega s T s, this is sine n omega s T p by 2, and this I can manipulate. So, basically to bring out these things so that I can get a sinc function. So, finally, if I just do that manipulation, I get T p by T s sinc n pi f s. So, I have put omega s equal to 2 pi f s into T p. So, this is what I get. Okay. So, the q n's are all being represented now. Now, what is we have got my q t s. Okay. So, So, what will be the corresponding frequency response, because QTS is nothing but this Qn e to the power this summation minus infinity plus infinity. So, they will just become impulse function at frequency domain at those frequencies n omega s or n fs. Okay. So, if I now means what we are trying to do is, if you just see this sample, QTS is getting multiplied with GT. Okay. So, if it is multiplication in, because we have already characterized the Fourier transform of this one, because we have got the Fourier series and then you do a transform, you will get all kinds of delta function with the strength as Qn, corresponding strength. Okay. So, now if these two signal are getting multiplied in time domain exactly to create this, so therefore, the Fourier transform of this one will be a convolution of GF and this one, fine. So, that if I represent that as G tilde f, that must be GF, which is the original message signal, convolution Tp by Ts sync n pi fs Tp. So, this n goes from minus infinity to plus infinity, and I have a delta at every fs, corresponding fs, right. So, this is the Fourier transform of that QTST, because it is just exponential. So, correspondingly he will be creating delta at every fs. So, I get, and the strength will be corresponding sync. So, this is what we get. Now, GF convoluted with this summation and this convolution, I can interexchange. So, GF can go inside, then GF convoluted with delta, again it becomes just GF minus NFS. So, I can write this as Tp by Ts summation n, so that should be sync n pi Fs Tp, and this becomes G of F minus NFS. Right. So, that happens to be my overall Fourier transform. Okay. So, now what you can see is this, that the Fourier transform is nothing but at every n. So, basically whenever n is equal to 0, I get GF. So, n equal to 0 means it is at the center frequency, n equal to 1 means right side, minus 1 means left side. So, like this. So, there will be frequency term which has, so it will be just exactly GF. So, the frequency spectrum remains the same, only thing is that it has a strength which is sync function, okay, and Tp by Ts. So, this sync function, what happens? This will be bigger and the next one will be smaller and so on. They just keep on going like this. So, this tip means the strength of them follows a sync function at every location of Fs. So, this is 0, this is Fs, this is minus Fs, and at every location of Fs the tip of them actually follows a sync function. So, what is happening? I am getting two advantage over here. One is that if I now employ, so this is still from minus b to plus b, I employ a low pass filter, this has no distortion because this is just exactly equivalent to GF with that sync multiplied. Okay. And the other advantage I get, if I do original sampling, what was happening? My power was getting distributed everywhere, right. Whereas here the central lobe, which is the lobe of my interest, is getting more power, and the side lobes, which I should reject anyway, are getting lesser power because it has a sync function. So, the overall strength of that follows a sync function. So, that is a good thing because most of the power are concentrated on the low pass band, and I will be employing a low pass filtering to take this. So, most of the power I will be getting while demodulating it, that is first thing. Second thing is, unlike the flat top sampling, it does not go through distortion. These are two most important advantage of this one, and it has another advantage which we can easily see, that because the strength of it is proportional to Tp. So, what is happening, as I increase my Tp, this strength in the central lobe will increase. Okay. That is a very good thing, because what will happen, as you increase Tp, there is also another counter effect. This Tp will increase, so this factor will increase, plus because it is a sink, this as you increase Tp, this will go to 0 very soon in the side lobe. So, basically the side lobes are getting decreased even more. So, what is happening, as I increase Tp, I will be getting more and more power over here. But let us try to see what happens if I increase Tp. Suppose I have a signal like this, I want to sample it. So, I sample it with these pulse, let us say 50% duty cycle. So, whatever this is, so my Tp is just half of Ts. Okay, so, this is Ts. So, what will happen? It will just follow the signal over this half, and then it will be 0, and then again over this half it will follow this, next will be 0. So, I have seen that as I increase Tp, of course, I will be getting more and more power concentrated over here, which is very obvious, because if I just make it full, that means Tp is equal to Ts, then the entire power, because it will just look like the same signal, entire power will come to my central lobe. But is that something I want? Probably not, because why we were doing sampling? We were doing sampling to get those get those sample values, and in between we are freeing the time to do time division multiplexing. So, more Tp we take, probably we will have less opportunity to multiplex anything else. So, there is a trade off between these, which we can immediately see. So, probably with this we have got a fair bit of understanding about natural and flat top sampling. These are the two most important sampling that are available practically. So, next what we will do, we will try to see what kind of circuitry we can put for doing this natural sampling. Okay. So, in the next class we will discuss a little bit of circuitry of these modulation techniques, and then we will probably go to digital version of this sampling or pulse amplitude modulation, which is called PCM. Okay, thank you.